What if I told you that a simple crystal could hold a memory? Not a memory of sounds or pictures, but of something totally invisible, radiation. In this explainer, we are going to uncover the incredible science behind these materials and their hidden, glowing memory. So let's just jump right in with a question that sounds, well, it sounds almost like magic, doesn't it? How can a tiny, unassuming little crystal actually prove that a life-saving cancer treatment worked? The answer reveals this amazing link between the simplest materials and some of our most advanced medicine. To understand how that's even possible, we first have to explore the super high-stakes world of measuring the invisible. This is a world where being precise isn't just a nice-to-have. It can literally be a matter of life and death. You see, in radiation therapy, you are walking an absolute razor's edge. The dose has to be just right. We're talking within a tiny 5% margin. If it's too low, the treatment won't work. If it's too high, you could damage healthy tissue. So in this world, precision is absolutely everything. And this need for precision goes way beyond the hospital. Just imagine a radiation accident. In all that chaos, the single most critical question you need to answer is, how much radiation were people exposed to? Getting that number right is the key to giving them the correct medical care and ultimately saving their lives. So here's the fundamental challenge, right? Ionizing radiation is this invisible force. You can't see it, you can't hear it, you can't feel it. So how on earth do you measure it? Well, the solution is ingenious, and it comes from materials that have a kind of superpower. They can actually store the radiation's energy and then release it later as a faint glow of light.
Okay, so how does this actually work? The easiest way to think about it is like a rechargeable battery, but it's a battery that gets charged up by radiation instead of electricity.
Now, the official scientific name for all this is luminescence dosimetry. It's a mouthful, I know, but it really just means measuring radiation by looking at light. And it all works thanks to a beautifully simple three-step process. First up, you've got the charge. When radiation hits the crystal, it knocks some electrons out of place, and they get stuck in these tiny imperfections in the material's structure. You can think of them like little traps. Next, you have storage. Those electrons are now locked in, creating a stable, physical record of how much radiation passed through. And the amazing part is, that record can last for days, months, even thousands of years. And finally, we get to read that record. We apply a stimulus, either heat or light, and that gives the electrons just enough of a kick to escape the traps. As they snap back to their original positions, they release that stored energy as a faint glow of light. Now, there are two main ways to trigger this light. The first one is called thermoluminescence, or TL. As the name suggests, the trigger is heat. You warm up the crystal, it glows, but here's the catch. That process completely erases the memory. The second method is optically stimulated luminescence, or OSL. Here, the trigger is light. This is a much gentler process, and it only uses up a tiny bit of the stored signal. That means you can actually reread the dose over and over again for verification, which is incredibly useful.
Okay, so we've got this faint glow. That's really cool. But a glow is one thing. Turning it into a precise scientific number is something else entirely. So how do we actually read the dose?
Well, the principle behind it is beautifully simple. The more radiation the material absorbed, the brighter it glows. That's it. It's a direct proportional relationship. More radiation equals more light. Now, of course, to make this proper science, we can't just say kind of bright or really bright. We need a standard unit of measurement, and that unit is called the gray. It measures the amount of radiation energy absorbed by a material, and it gives us a precise universal language to talk about dose. So for thermoluminescence, the measurement isn't just a single quick flash. As the material gets hotter and hotter, we see this signature pattern of light emerge. It's called a glow curve because the intensity of the glow changes with the temperature. The light intensity rises to a very distinct peak and then it falls away. The key thing to understand here is that the total amount of light that's given off, basically the area under this curve, tells scientists the exact radiation dose that material absorbed. With OSL, the story is told a little differently, through what's called a decay curve. Remember, instead of heat, we're using light to stimulate the crystal, and what we're measuring is how that initial bright flash of light fades over time. You can see that decay right here. The light starts out super bright, and then it drops off pretty quickly. But the crucial measurement, the one that tells us everything we need to know, is the intensity of that very first flash, right at the beginning. Its brightness is directly proportional to the radiation dose. Simple as that. So that's the physics. But why does this glowing memory matter? Well, this is where the science gets truly incredible when we see how it's being used out in the real world. And this brings us right back to our opening question about cancer therapy. These tiny crystals become the ultimate fact checkers. They're small enough to be placed right on a patient's skin or even inside the body, and they provide a direct physical record of the radiation dose. They are the final guarantee that a life-saving treatment was delivered exactly as it was planned. In a radiation emergency, this technology becomes a kind of forensic science. I mean, what if the clue to how much radiation you received was sitting right there in your pocket? Scientists can actually read the glowing memory from the electronic bits inside your phone, or even from things like dental fillings, turning everyday objects into accidental witnesses that hold a precise record of exposure. This memory can last for thousands of years, which basically turns these materials into tiny little clocks. Archaeologists can measure all the natural background radiation a piece of pottery has soaked up since it was last fired in a kiln. In effect, they can ask the artifact, hey, when were you made? And its glow gives them the answer, unlocking secrets of the past. You know, the same tech that dates the past also helps protect our future in space. Astronauts are constantly dealing with cosmic radiation, and these tiny glowing memories are their personal record keepers. They track exposure, they help manage health risks, and they give us the data we need to design safer ships for the journey to Mars and beyond. So what does the future hold for these remarkable glowing materials? Well, let me tell you, their journey is far from over. The future of this research is happening at the atomic level. Scientists are using techniques like band gap engineering, which is really just a fancy way of saying they're customizing a material's atomic structure. By adding tiny, precise impurities, they can design brand new crystals from the ground up that are way more sensitive and stable than anything we have today. And this leaves us with a final provocative question. We have taught simple crystals to remember an invisible force. If they can remember radiation with this much precision, what else could we teach the materials of the future to remember? Pressure? Temperature? Chemical exposure? The possibilities are just beginning to glow. Thanks for joining this explainer.